Heaps are, first of all, complete binary trees. If you remember from the previous lecture on binary tree, a complete binary tree may have missing nodes only on the right side of the deepest level. So as an example, you see a binary tree here. You see that at every level except the last level, we have the maximum number of nodes possible for that level. And on the deepest level, all the leaves are as far to the left as possible. So a heap is a complete binary tree with the heap order property. Now, what is the heap order property? We have two different kinds of heaps. We either have min heap or max heap. In a min heap, the value of each node is less than or equal its child values, its children values. And in a max heap, the value of each node is greater than or equal its children's values. A binary heap with all keys equal is both a min heap and a max heap. So in a heap we can have duplication. And we say that a heap is partially ordered. The node values in a heap are partially ordered, as opposed to binary search tree where it is fully ordered. We usually represent heaps using arrays, and array-based complete binary tree is usually the representation that we use for heaps. There is also a recursive definition for a heap. A heap is a complete binary tree that's either empty or whose root contains a value, a search key, greater than or equal to the search key in each of its children. This is for the max heap, and whose root has heaps as its subtrees. So it means that for a heap, all the subtrees are also heaps. So this is the recursive definition of a heap. Be careful that this use of the word heap is entirely different from the heap used in memory allocation. Several authors began using the term heap in 1970s to call the pool of available memory. So we use heaps in data structure, and we also use it in memory allocation. They're two entirely different topics. Binary heaps have two properties, namely a structural property, which is like being a complete binary tree, and a heap order property, which we mentioned for max heap and min heap. The structural property of a heap is a binary tree that is completely filled, with the possible exception of the lowest level, of the deepest level, which is filled from left to right. Such a tree is known as a complete binary tree, as you know. This is an example of the structural property of a heap, which you see that we have a complete binary tree. If we use array-based implementation of tree, we know that for any element in array position I, the left child is in position 2i. In position 2i, if we start numbering the positions from position I, but if the index starts from 0, it's going to be at index 2i plus 1. And the right child is in the cell after the left child, so it's going to be at 2i plus 1 if we start the index, or if we start numbering the positions from 1, and it's going to be at index 2i plus 2 where indices start from 0. and the parent is in the position floor of I over 2. Again, this is where I starts from 1, or index I minus 1 over 2 and floor of that. Okay. So in literature, there are two different kinds of array-based implementation used for heaps. One that starts from 0, similar to what we do in arrays and vectors in C++ and many programming languages. So the index starts from 0. And in many applications, in many implementations, um, programmers leave the first location of the array empty, which is index 0, and starts the heap from index 1. Okay, so if the heap start at index I equal to 0, you can find its parents left child and right child based on these formulas. And if the heap starts at index 1, we can find the parent and left child and right child location using these formulas. A heap order property. So the second property of a heap is the order property. As mentioned in the first slide, the property allows operation to be performed quickly is the heap order property. Since we want to be able to find the minimum or the maximum quickly, it makes sense that the smallest element or the largest element for max heap should be at the root. So if we have a min heap, the smallest element would be at the root, and if we have a max heap, the largest element would be at the root. If we consider that any subtree should also be a heap, then any node should be smaller than all its descendants. This is again for a min heap. Or every node should be larger than all its descendants in a max heap. The search key of the children have no relationship. It means that the siblings do not have any relationship. You don't know which one is larger or smaller. The heap is always complete and therefore balanced. You know that like every complete binary tree is also balanced. Applying this logic, we arrive at the heap order property. In a heap, for every node x, the key value in the parent of x is smaller than or equal to the key in x, except for the root because it doesn't have any parent. And again, this was for the min heap. For the max heap, you just like have to replace the smaller with larger. Okay, so this property is also called partial ordering. The same definition for a max heap. We declare a max heap, which enables us to efficiently find and remove the maximum element by changing the heap order property. And we will see that an application of heap, which is priority queue, can be used to find either a minimum or a maximum a bunch of elements that we have in the heap. But this needs to be decided ahead of time. So we have to know, like, we want to find a minimum or maximum. We want to have a min heap or a max heap. We can use the heap to implement the priority queue, which will be discussed soon. So we represent heaps as an array. An array that represents a heap is an array with two attributes. It has a length, which is the number of elements in the array. So it's basically the maximum size that we can have. And the heap size, the number of heap elements stored in the array. Okay, so heap size should be always smaller than the length. So we in the videos discussing binary trees, I mentioned how we can implement a binary tree using an array. So we just start from the highest level with the lowest level and go up to the deepest level and start filling out the array from left to right. So you see that if this is our binary tree, we can implement an array. We can represent this binary tree using an array by going from top to the bottom, from the lowest level to the deepest level. From the highest level to the deepest level. So 16, 14, 10, 8, 7, 9, 3, 2, 4, 1, and we just like fill out the array like that. And again, I should emphasize that there are two conventions for using the array and the indices of the using the heap and putting values for the indices of the heap. In one convention we start from 0, in another convention we start from 1, and you'll see that again, like the table that shows you the formulas for finding the parent or left child and right child in a binary tree represented as an array. The root of the tree is stored at A0, its left child it's going to be at A1, its right child at A2 if you're using the indices starting from 0. And in the array representation of heaps, we don't have any pointers. So that's one of the advantages. We don't have any space overhead. We don't have like any memory wasted for pointers. The second advantage would be locating the every node's parent and left child and right child very easily. And the one thing that you should know that like sometimes when we want to be more computationally efficient, instead of calculating 2 times I or I divided by 2, for calculating 2 times I, we just basically shift all the bits one to the left. So this is the left shift operator. So if you like represent a number in a binary basis, in a binary format, if you shift all the bits one to the left, it's basically the same as multiplying that number by 2. And if you shifted one to the right, it's basically the same as dividing that number by 2. You can just verify that by like finding a binary representation of number and like see what happens if you multiply it by 2, and like is it the same as like shifting all the bits one to the left, and the same thing for I divided by 2 and shifting all the numbers one to the right. So this is one of the reasons that some people prefer using this representation and leaving the first element of the array empty, so that like you can just like you use like faster computational methods. The other way is like basically makes like the calculation and remembering formulas easier if you start from 1. In this presentation, I use the second convention because it's just like most programming languages. For most programming languages, the index of an array starts from 0, and there's no real need to leave one array element empty. Okay, so like there's no need to waste this memory location. So like I use the second convention where the indices start from 0. So the length of a heap is basically the number of elements in an array. So we usually like fix the size of the array, and the heap size is the number of elements stored in the heap, in the array. So number of elements in heap stored in the array. And heap size always is smaller than or equal length of A. Okay. So you'll see that, for example, for this one, the length of the array might be 15, right? But the size of it is 10 because we only have 10 elements in our binary tree, in our heap. So as a reminder, height of a node in a tree is the number of edges on the longest path downward to the leaf, to the deepest leaf. That would be the height of a node. So it's the maximum or the longest downward path from the node to a leaf. And height of a tree, it's the height of its root. We can calculate the height of a heap very easily. It's because like a heap is a complete binary tree. Its height is basically in the order of log of n base 2, and the exact formula is given here, is basically log of n plus 1 in base 2, the ceiling of that minus 1. We usually don't use this formula. We only need to know that the height of a heap, or the height of a complete binary tree, or even the height of a full binary tree, it's in the order of log n. So basically, because of that, basic operations on a heap run in order of log n, big O notation log n. The other important property of a heap is that a number of leaves, this is also true for a complete binary tree, the number of leaves in a heap is the ceiling of n over 2. So if you have n nodes in your heap, you would have 5 leaves. If you have 11, you would have 6. And the elements in the subarray A, starting from floor of n over 2 all the way to the last element, which is index n minus 1, are leaves. So in the array representation, you will see that all the leaves would be at the end of the array. Okay, so if I use this formula, you see that the leaves start from n over 2 going all the way to n minus 1. So in this one, n is 10. I'm using this convention, right? This convention. So the leaves start from index 5. From index 5, right? So like you see that like it's number 9, right? Number 9 is index 5. Here like I'm using the second convention, but like the leaves start from number 9, which is index 5, and it goes all the way to index n minus 1, which is number 9. So you see that like all these nodes here at the end of the array, 9, 3, 2, 4, 1, are the leaves. And the starting part of the array are the internal nodes. So here you see some examples. This one is a max heap. First of all, it's a complete binary tree. It also has the order property. Every node has a value which is bigger than or equal its children. So 99 is bigger than 18 and 95, 18 is bigger than 15 and 10, 95 is bigger than 80 and 30. And this one is also a max heap. This is a min heap because 5 is smaller than all its children's values, and 8 is smaller than 9 and 95. 9 is smaller than 18 and 10. So you see that every node's value, key value, it's smaller than or equal all its descendants value, and this property is valid for every node. Again, you see like a review of the concept of level or depth and how we store a tree into how we represent a tree in an array. Like we start from index 0 from the root, and we go from the highest level to the deepest level, and we start numbering the nodes from left to right. So 0, 1, 2, 3, 4, 5, 6, 7, and 8. This is the root, and this is the index. And again, just be careful that like in many implementation, many textbooks on like different videos on internet, some people start this index from 1, as you saw in this representation. That confused me a little bit. For structural property or structural constraints of heap, you see that all these three binary trees on the top, they are complete, right? So they satisfy the structural property of the heap. However, these three at the bottom, they're not complete, because you see that first of all, for this one, you see that at the lowest level, at the deepest level, the leaves are not as far to the left as possible. For this one, you see that from the top level all the way to the second bottom level, all the levels, they should have the maximum number of nodes. This one does, level 0 does, level 1 does, but level 2 doesn't. It could have like 4 nodes, but it only has 2. And for this one, you'll see that this one is also not a complete binary tree, because the although like it satisfies like the first condition of complete binary tree, where all the levels from top to the second to the bottom level should have maximum number of nodes, which is true for this one, but all the leaves at the bottom level are supposed to be as far to the left as possible, which is not the case for this one. So these three are not heaps. And this picture here shows the growth of a heap as the number of nodes is increased. So if you only have one node, this is like your heap. If you have 2 nodes, that would be your heap, the structural the topology of your heap. This one would be like a complete binary tree or a heap with 3 nodes, and so on. As you see, like the shows like the topology of complete binary trees as the number of nodes increase. Also like the heap order constraint, so you'll see that let's say like we want to talk about max heap. So this one is a max heap. First of all, it is like all of these are complete binary trees. For this one, you'll see that every node is greater than or equal all its descendants. The same thing for this one, the same thing for this one. However, for this binary tree here, although it is complete, it doesn't satisfy the order constraint. So you see that like 45 is not bigger than 55, or 55 is not bigger than 58. So it's not a max heap. It's not a min heap either. Okay. The same thing for this one. This is not a max heap, because for this node doesn't satisfy the heap order property. So 25 is not bigger than 34. And the same thing for this one. 45 is not bigger than 55. So these are not heaps. More examples here. So this one shows a min heap, right? First of all, it is a complete binary tree, and the value of every node is smaller than or equal all its descendants values. This one is not a heap, it's not a min heap, it's not a max heap either. You see that because for this node, this is like has a value greater than its left child, so this is not a min heap. The same thing for this one, this doesn't satisfy the structural property of a heap, right? It's missing the last level. The nodes are not as far to the left as possible. If this 32 was the left child of 31, then we would have a min heap like what we have here. But if it's the right child, then it doesn't satisfy the structural property of heap. And this is also not satisfying the structural property of heap, because at this level, which is the second to the bottom level, we don't have the maximum number of nodes. We were supposed to have 4 nodes, we only have 3. The same thing for max heap. This one is a max heap. It satisfies both structural and order property. This one is not a heap. It satisfies the structural property, but it violates the order property, and these two violate the structural property, so they're not heaps. So let's assume that we have this binary tree. So first of all, let's look at it. Is this a heap? And if it is it min heap or max heap? It is a complete binary tree, and you'll see that every node is smaller than or equal its descendants values, right? So it is a min heap. So for this one, where is the minimal element? So we know that the smallest element for a min heap, it's going to be at its root, right? And for max heap, the largest element would be at the root. For a min heap, where is the maximum element, right? So the maximal element should be one of the leaves, right? Should be one of the leaves, right? So should be in the second half of the array. Okay. We talked about this one, how many leaves we have in an n node heap, right? I showed you the formula for that. What is the complexity of finding a maximum in a min heap, right? So because we know that the maximum in a min heap, it's gonna be in the second half of the array, so we basically have to just go through the half of the array, the second half of the array. So it's just going to be n over 2, or it's going to be order of n. Now where is the second smallest element? Think about this one, right? Think about this one, right? So where is the second smallest element? You can just like think about this and see where the second smallest element should be at. So this also reviews what I mentioned about locating the parent of a node at index I, or the left child of a node at index I, or the right child of a node at index I. There are two different conventions. In one convention where I starts from 1, you can use these formulas. And in the convention that I starts from 0, you can use this convention. In this presentation, I use the second one, this one, where we start filling out the array from index 0. So our heap starts from index 0 of the array. Okay, operations on heaps. So all heap operations are based on the following idea. So we either want to make a simple, we want to make a simple structural modification to the heap. We either want to insert a node or delete a node, so different changes for different operations, and it might result in a violation of the heap condition. Okay, so if you insert a node or delete a node, it might violate the heap condition, either the structural um, or the heap order property. So we have to make sure that whenever we make a change, whenever we do an operation on a heap, we basically make sure that um, we just like keep the heap property, both structural and the order property. Another operation that we can have, just traversing the heap from the root to the bottom, or from bottom to the root, depending on the operation. Okay, so we have a top bottom or top down approach, or a bottom up approach. So like depending on the operation that we have, we might need to go traverse the heap from root to the bottom, or from bottom to the root. We'll see like more about these two operations throughout this presentation. The most important operations on heaps are inserting an item, removing an item, creating a heap from an unordered array. So we have like an array when we want to create a heap out of that. Sort an array. We'll see that like one of the applications of heaps is basically sorting an array, finding the minimum or maximum, and changing the values of nodes. Like we say like key values of heap nodes. The basic operation on heaps run in time at most proportional to the height of the tree. And we mentioned that for a complete binary tree, and therefore for a heap, the height of a complete binary tree is of order log n, right? So that's why like all the basic operations are going to be as fast as order of log n. A node in a complete binary tree has the heap property if the value in the node is as large or as larger is larger or as large as the values in its children. So this is like for the max heap property. For the min heap would be as small or smaller than the values in its children. And therefore like all leaves or terminal nodes, they have the heap property, heap order property. Why? Because like they don't have any children, right? So like it has only one node. And a binary tree is a heap, a complete binary tree is a heap if all nodes in it have the heap property. I have to make a change here. A complete binary tree is a heap if all nodes in it have the heap property. So for example, for this one, 8 and 14, they have the heap order property, but 12 doesn't, right? This one is not a max heap, right? It's also not a min heap. So it doesn't have the max heap or min heap property. So one important concept is that after we do operations on the heap, we have to make sure to maintain the heap property. Suppose that we have two subtrees that are max heaps, but the root violates the max heap. We just have to fix the offending node, fix the node that doesn't satisfy the heap property, to maintain the the heap order property and make sure that this tree is heap. Okay, so in this case, we find the offending node, and by exchanging the value at the node with the larger of its children, right? So like, let's say like we have a max heap and we have a node that's smaller than these two. These two subtrees are already heaps, but this is not like, let's say like both of them are max heaps, but this node, this root is not bigger than the both children. So what we have to do in this case, we just basically have to compare the left child and right child and see which one is larger, and basically try like swapping or sliding this root down, or like the official term is like bubble it down, and to maintain the heap order property. And like we have to continue doing that recursively so that all the nodes satisfy the max heap property. We'll go through this concept using many examples, so if it's vague at this point, don't worry about it. We're gonna see like lots of examples for this topic. So the first operation that we have to do on heaps, or we might do on heaps, is inserting a node to a heap. To insert an element X into the heap, we create a hole in the next available location, since otherwise the tree will not be complete. So what does that mean? It means that if we have a heap like this, if we want to insert a node here, its next location, available location, would be just the right child of 31, right? The right child of 31. So like we insert the node here, okay? And if you see like in the array representation, would be like inserting an element at the end of the array. Okay, so that's what this sentence means. And if we do that, we make sure that the binary tree is complete, so the structural property of the heap is satisfied. If X can be placed in a hole, in the hole, without violating the heap order property, then we are done, right? Otherwise, we slide the elements that is in the hole's parents node into the hole and bubble that hole up towards the root. This concept is called bubbling up, or trickling up, or sift up, or percolate up. There are many different terms for it. Reheapification up. So like different textbooks might use different term for it. And we continue this process until X can be placed in the hole. It means like either we go all the way to the root, or we get to a point that X is basically like satisfies the heap order property, right? So let's look at this concept using this example. So we have an original complete binary tree which satisfies the min heap order property. So this is a min heap, right? You see that it's a complete binary tree and every node's value is smaller than its children's values, right? So let's say that we want to insert 14, right? Can I insert it here? Right? If I insert 14 here, it would violate the structural property of the heap, right? So what we do, we always insert it at the next available location on the last level. So here would be inserting it as the right child of 31. Okay, so this is basically what happens here. Okay, now in this case, the structural property of heap is satisfied but its order property is not satisfied because this is a mean heap. Every node is supposed to be smaller than its descendants values, but you see that 31 is not smaller than 14. So what we do, we compare 14 and 31, right? And in this case, you see that we swap them. So 14 basically bubbled up here. We're going up. This is like bottom up approach. So, so you see that for insertion, we insert the node at the last possible location to make sure that the structural property is satisfied. And after that, from that leaf, we bubble up towards the root until we get to a point that the heap order property is satisfied. So at this case, 14 is smaller than 31, so we swap them. And then we have, like at this point, we have 14 here. Now we just like go all the way up, right? So like we compare now 14 and 21. Again, these two are not at the right place. So like we swap them. So 14 goes up and 21 goes down. And at this point, we compare 14 and 13, right? And this doesn't violate the heap order property. 13 is smaller than 14. So we are done. We are done. So this is the procedure for inserting a node to a heap. We insert it at the next available location on the bottom level, right? And then we bubble up or trickle up or reheapification up or sift up. There are many different terms for it. Another example you see here. So in this example, we're looking at the same example, but you see that instead of swapping, there is a more efficient way of doing bubble up, right? So what we do, we insert a hole, we create a hole at the next possible location, right? So this is like, imagine this is a hole. Now what we do, we have the value of the node that we want to insert. It's 14. So what we do, we compare 14 and 31, right? So 31 is bigger than 14 and we have a mean heap, right? So it violates the mean heap order property. So what we do, we slide this parent down. We move it down, right? Right? We didn't swap any elements because we didn't insert 14 into the hole, right? So like we just like move the parent one level down. Okay, and then again we compare 14 and 21, right? Again 14 is smaller than 21, so like it shouldn't be here, right? So what we do again, we slide this parent one level down, so 21 comes here, like we have a hole here. Now again we compare 14 and 13, right? So this time 14 is bigger than 13, right? So our loop or our recursion ends here. We have a hole, we insert 14 at the correct location. And how this is going to be done algorithmically, like, and how can we program this, like using the array implementation of heap. We know that we are gonna insert the node at the next, or insert the hole at the next possible location, so it would be just like at the end of the array, right, after the last element, right? And like using the formulas that were shown in previous slides, like for this node we can find its parent very easily, right? So if this is at index 10, right, its parent it's gonna be at this index. It's going to be at the floor of n minus 1 over 2. N minus 1 over 2, it's going to be 9 over 2, which is going to be a floor of it, it's going to be 4. So we find the parent and we compare the parent's value with the value that we want to insert. This is greater than 14, so we slide this one down, right? And then now we go to this node, right, and we find the parent of this one now, parent of this hole. This is at index 4, so its parent, it's going to be at the floor of 4 minus 1 divided by 2. It's going to be floor of 3 over 2, which is going to be 1. Okay, so again, what we do, we slide this one down, like, because 21 was bigger than 14, we have a min heap. And again, at this point, we find the parent of this one, which is going to be the root, right? We compare 13 and 14, right? This is smaller than 14, so our loop or our recursion stops at this point, and we insert 14 at this hole. Okay, so this is showing like what happened and like how now we have a new heap, right? So the size of our array was increased by 1, right? And you see that some nodes were moved so that we maintain the heap order property. For the insertion running time, in the worst case is that like when insert, like we have to go all the way up to the root. So how many comparisons do we have to make in the worst case? It's going to be of order log n. In the worst case, we have to go all the way up to the root, right? And because the height of a complete binary tree and a height of a heap is in the order of log n, the maximum number of comparisons we have to make, it's going to be order of log n as well. And this shows the implementation of this algorithm. Basically, it's a pseudocode that shows the implementation of this algorithm. So like here you see that like we incremented the size of our heap, right? We start from the last element. Okay, so again, like I noticed a mistake here. Okay, so we start from the last index and we move all the way to the root, so we bubble up, right? So like we start like checking the value that we want to insert and the parent's value, and like we find the parent's value using the formula I showed you earlier, and then we make a comparison. If there is a need for the for sliding the parents down, we do that here, right? So we do that here, and otherwise, once we get out of the loop, we just insert the value that we wanted to, the key value that we wanted to insert into the heap at the hole that was created. Another example, you see like here we have like for every node we have a pair, so we call like key value pair, right? So here this is like the value that we're going to use to compare the nodes, right? So here like you see that like we have like 2 is as the key value, and like for this node 5, and this one 9, and this one is also 9. So this one like before like inserting the node which contains the string gem and also contains the key value 1, you see that like before inserting that we had a min heap, right, we insert this node, right, with the key value 1 and the string value gem, right. um, this satisfies the structural property of binary tree, but one thing that's missing is the heap order property. So we have to start from here and go all the way to the root. We compare 1 and 5. 5 is bigger, so it comes down, like you just like swapped here. But again, I mentioned that like you can, instead of swapping, you can just like create a hole like and slide your slide the parents um, down, like um, instead of just swapping the elements. So this is basically what happened here. We slide we like here, like it's basically swapping um, 5 and 1, like so 1 goes here, 5 comes here, right. We haven't reached the root yet, so we have one more comparison, right. So like in this case again, 1 is smaller than 2, so this is what we end up with. Okay, so this is like how we make sure that we re-heapify our heap after inserting an element into it, or inserting a node into it. Okay, this one shows another example like that. We have a min heap and we want to insert 8. We insert it right here, okay, at the next available location, right. So it's going to be next to the last leaf that we have, right. So then, right, because we want to have a min heap, right, so we start comparing this value that got inserted with the parent nodes. 13 and 8, we're going to compare them. So 13 is bigger than 8, we swap. 8 and 10, right, 10 is bigger than 8, swap. And then we get to 6 and 8, and there's no need for swap, so we are done. This is now our new heap. Okay, this shows you the algorithm for implementing that using swapping, but again, I'm sorry, please note that to make the program more efficient, you can call pull parent down, like pulling the parents down, instead of calling swap, right. And we find a place for the new key, move the hole down upward, sorry, move the hole upward, so bubble up the hole when needed, and at the end put the key value into the hole. So this is exactly what we did in this case. Right, so like we just like put 31 in the hole, and then 21 in the hole, and then 14 goes at index 1. This shows another example again. We like this time we inserting 18, and this one again is a min heap, right. After inserting 18, the heap order property is violated. We swap 18 and 31, and then 18 and 21, right. And sorry, like here, like we insert like 18 here, we swapped 18 and 31, and now we compare 18 and 21 again. 21 is supposed to be smaller than both its children, which is not the case here. So what we do is swap 18 and 21, and finally, like when we have 18 here and 21 here and 13 here, right, again 18 is not smaller than or equal 13, so like again we're gonna be actually, like, sorry, that's okay. Like once we get to the point that this is 18 and this is 21, this satisfies the heap order property. So like once we get to this point, we are done, right, because we compare 18 and 13 13 is smaller than 18, so everything is good now. So this is basically the final heap after inserting and number 18 to it. This shows the insertion using another example. In this implementation, we're using, instead of swapping, we just like use that whole concept, right? So like here we had a binary heap, we inserted 41, like, or you can assume that this is like a whole, but we have 42, we have 42, and we compare 42 and 27, right? And this is a max heap, this one is a max heap, right? So we compare 42 and 27 because this is a max heap. Every node's value should be greater than or equal its descendant's value, which is not the case here. So what we do, we slide 27 down, we compare 42 and 35, and that's basically like satisfies the heap order property. There is no need for us to go up anymore, right? So we stop right here, and this is what we end up at. This implementation shows like how you can insert, but this time like it doesn't use swapping. So please go through it. There might be some mistakes here. If you find any mistakes, please let me know. But basically this is what it is. We find the maximum element, and we insert a node at the last possible location, um, uh, next to the last leaf, right? Next to the last leaf. So it's going to be, at the first possible location next to the last leaf, right? And we start bubbling up, or trickle up, or sift up, or percolate up, right? And this shows you how you can implement this insertion method. So the algorithm is also given here, so like we can implement it non-recursively using loops, or we can also use loops, right? So here this one basically shows like how we can bubble up, right? If you're given an index of the array, which represents a node itself, then we can just like bubble up, and we keep doing that until we get to the point that we are either at the root or at the point that array I is bigger than array parent, right? So this is like we make sure that like this happens. If we get to the point that array I is bigger than array parent, right, and I is bigger than 0, right, it means that we haven't got to the end of the array, right? So we just like what we do, we just like do swapping, and we start doing that again. We start bubbling up, but this time instead of starting from I, we start from its parent, right? So like we can find the parent of a node very easily using an array-based implementation. The second operation that we'll see in this lecture is deleting a node. Delete is handled in a very similar manner as insertion. However, finding the minimum, while finding the minimum is easy, the hard part is removing it, right? We mentioned that if we have a min heap, we know that at the root we have the the smallest element, or if we have a max heap, at the root we have the largest element, right? So like we can find the minimum or maximum in a min or max heap very easily. The hard part is removing it, because if we remove it, the structural property doesn't maintain anymore. So when the minimum is removed, a hole is created at the root. Since the heap now becomes one smaller, it follows that the last element in the heap must move somewhere in the heap, right? So if x can be placed in the hole, then we are done. Otherwise, what we do, we slide the smaller of the hole's children into the hole. So this time we bubble down, or trickle down, or percolate down, or sift down. Okay, so and we repeat this process until x can be placed in a hole. So again, the action required for this operation is going to be order of log n as well. So our action is to place x in its correct spot along a path from root containing minimum children. So removing from a heap always happens from the top, so we always remove the root. It's going to be the minimum element for a min heap, or maximum element for the max heap. Okay, once we do that, we have a hole right at the root. We have a hole. So what we do, we just fill the hole with the last item. So the last item in the array, we switch it with the with the where was I? So we remove the node, we leave a hole, fill the hole with the last item. Okay, and this makes sure that the heap structural property is preserved. And this time we compare the node that just like jumped to the root. We compare that node's value with its children value. Okay, if there is any need for swapping or sliding the parents down, we do so. Okay, some of the operations are like removing a minimum element in a min heap, maintaining heap shape, maintaining heap order. So these are the steps that we have to take in order to remove an item from a heap. So to maintain heap shape, actual node removed is the last one. Okay, to maintain heap shape, actual node removed is last one in the array. And we replace root value with the value from the last node, and then delete the last node. And we do this recursively. We sift down, or bubble down, or trickle down to the new root value, and we continue doing that with the smaller child until no child is smaller, or we reach the leaf. Okay, there's so much text here. Hopefully doing this using example make it more understandable. So here, like, this is the original heap that we have. It's a complete binary tree. If I look at the key values, also I see that it satisfies the min heap order property. So in deleting from a heap, we always delete from the top, right? Because like we basically want to have like either the smallest number if we have a min heap, or we want to have the largest number if you have a max heap. So this is gonna be done. So this node is gonna be done. is going to be gone from, it's going to be removed from the tree. So like here, like we have a hole here. We can store this in a temporary variable or temporary object, and we'll see in the next video why we want to do that. Whenever we delete the root of the heap, we can store this in a temporary variable. But like in this hole, like I should fill it out with another node. So what I do, I compare the key value of the children of the node that just got deleted. So that's 2 and 9. Okay, we want to have a max heap, right? We want to have a max heap, right? So once we removed the root node, we replaced the hole with the last node in our heap. What's the last node? It's gonna be the most right leaf, the most right leaf, right? So we're gonna replace it with the last. We're gonna replace the last. We're gonna replace the hole that we have with the last node. This is going to be the last node in the array representation as well. Okay, and we can keep this one in a temporary variable. We can use it later on, as you see, for heap sort. Okay, so 5 goes here. Now here, like we remove the node, we remove the root, right? The structural property is maintained. Structural property is maintained. Why is it maintained? Because like we removed this node, right? If I wanted to remove this one or this one or this one, the structural property wouldn't maintain. So that's why like we remove the most right leaf, right? And this one comes up right here. Now we have a complete binary tree, but this one doesn't satisfy the max heap property. So now what we have to do, as opposed to the insertion method that we went from bottom to the up, we bubbled up or trickled up. Now we have to bubble down. We have to go down from top to the bottom. So what we do, we first compare the left child and right child of this new root, right? 2 and 9. 9 is the bigger. So what I do, I swap 9 and 5. So 9 goes on top, 5 comes at the bottom. I made a mistake, sorry. I made a mistake. Oh, sorry, this is a min heap, not a max heap, right? So in a min heap, again, I compare these two children. 2 is smaller, so 2 is gonna go up, 5 goes down. Right now, I still have to compare 5 and 9. 5 is smaller than 9, so it's at the correct location. So then I stop here. This is the new heap that I have after I inserted the root. So root is removed. Then the tree must be updated. So root is exchanged with the last leaf, but it's removed from the tree. And then we now perform bubble down. In bubble down, heavy node trades place with its lighter child. Okay, so that would be the other way around if we have, like, instead of min heap, we have max heap. So like we have to just basically compare the children, right? Like in this case, compare the children of this node, right? Here, because we have a min heap, the smallest one would replace the root, and 5, it's gonna slide down here. So like we basically swap these two nodes. Another example here, so this time we want to again delete, right? It's the same as dequeue, right? So we want to dequeue or delete or pop, right? We always delete from the root. That's like how it's going to be done for the heap. So first of all, pay attention to this one. This is a max heap. So we remove this one. What do we replace it with? We replace it with the last leaf or the most right leaf. So 83 goes here. Now what we have to do, we just like compare left child and right child of 83, right? This one is bigger, so we swap 93 and 83. So 93 comes here, 83 comes here. Okay, and we have to go all the way down to the leaf, or like we stop where the heap property, heap order property is maintained. Now let's look at this one. Does this satisfy the heap order property? No. So again, what we have to do, we basically have to uh, move 90 here, and then 83 goes here. Okay, and then like again, like we compare 83 and like we compare 42 and 55. 55 is smaller. We compare 83 and 55. 83 is at the correct location. So like what we did, we just like we put 93 here, and then 83, and then sorry, 93 and then 90 and then 80, 83. So similar to the insertion method um, for the deletion, right? For the deletion or for dequeuing, the order of comparisons, it's going to be big O of uh, height of the complete binary tree, or height of our heap, which we know that it's in the order of log n. But just notice that when we delete, we actually make more comparisons, because like we also have to compare two children, and then compare the biggest one with our new root, and then do the same process recursively, or like using a loop, right? So the number of comparisons is more than insertion. It has the same big O notation, but we, like in the worst case, might have twice number, like 2 times number of comparisons that we had for insertion, because like for every iteration or for every recursion, we have to compare the left child and right child, as well as like comparing like their maximum or minimum with the like new root or the newly inserted node. Okay, again, look at this one, right? We delete 6, we replace 25 like with 6, right? So like here the structural property is maintained, right? So this was a mean heap, right? So we want to make sure that this would also be a mean heap, like we want to maintain the mean heap order property. So compare 7 and 10. 7 is a smaller, right? So we swap 7 and 25. 25 slides down. Then we compare 9 and 21. 9 is a smaller, like we compare 9 and 25. 9 is smaller, so we swap 9 and 25, and that's what we end up here, right? And we bubbled down until we got to the leaf, so that's when we stop. Okay, so again, like some questions here, like if you have a min heap, where is the minimum element? Like how did we maintain the shape? Like how did we make sure that after deletion the binary tree would still have the heap structural property, right? By removing the last element, and sorry, by replacing the root with the last leaf, right? So that's what we did. And after moving last element, right, we have to make sure that the whole tree would also have the would have the heap order property. Just like something to let you know that like a tree like this second one that you see here, you see that the left subtree of the root is a heap, the right subtree of the root is also a heap. This is called a semi-heap, right? We call this a semi-heap, that the root doesn't have the heap order property, but both its left subtree and right subtree are heap. That this is called a semi-heap. So after like moving the last element to the root, we basically we ended up with a semi-heap, right? We want to make sure that the heap order property is satisfied, and this one we're just gonna do bubble down, right? So like and instead of swapping, again you can implement this more efficiently, like so, like keeping 25 like in a temporary variable and like comparing them with their children, and then pull the correct child or like the appropriate child up, right? So like pull it up, right? So like move 7 here and then 9 here and then 25 goes here. So we stop reheaping or reheapification or bubble down or trickle down or sift down when we reach a leaf, or we get to a point that the heap order property is already maintained. So that's going to be our base case if we have a recursive implementation, or like this is going to be the condition to get out of the loop if we have a non-recursive implementation. I'll show you another example here. We have this one, like this is the array representation. We remove the root 5, which is the last element in the array. It's going to move to the root. So this is what we end up with. This is called a semi-heap. The left subtree is a heap, the right subtree is a heap, but the whole tree is not. Okay, so we just like basically have to transform this semi-heap back into a heap, like so. Like what we do is basically bubble down, right? So we find like this was a max heap, right? So like we still want this one to be a max heap. So we compare 9 and 6. 9 is bigger, so we swap 9 and 5. Or you can think of like we are basically pulling this child up. We're pulling this child up, okay? And then again we compare 2 and 3. We find the largest one, right? This is the one, and we compare it with 5, right? We compare it with 5, and then like this one already satisfies the heap order property. So like this is like a heap, right? So like we don't have to go any further. It shows you the process here. So the same example that we did insertion on, let's do a deleting on, right? So like here we're gonna delete the root, right? 31 is gonna replace the root, right? We have a hole here, right? So 31 is gonna delete, it's gonna replace the root, right? And then we can like swap them, or like in a better way, like this hole, right? We can just pull the child up instead of swapping the elements, so that we have a more efficient implementation. Since this is a min heap, right, we compare 14 and 16. 14 is the smaller one, so then we compare 14 and 31. 14 is smaller than 31, so we're gonna pull this child up, So 14 is gonna move here, right? Now, right? So then what we do, like for the children of this heap, we're gonna compare them, right? 19 and 21. 19 is smaller, so we find the smallest of the children. Now we compare 19 and 31. Again, 19 is smaller, so what we're gonna do, we're gonna pull this up. So 19 moves here, okay? And again, for this whole, we compare its children, 26 and 65. Excuse me. 26 is smaller, so we are gonna pull this 26 up. 26 and 65, 26 is smaller, 26 is also smaller than 31, so we're gonna pull this up. Now we got to the leaf and we have an empty hole, so we're gonna insert 31 here. Okay, so you see, like if we do this algorithm, we don't need to do any swapping, so it's a little bit more efficient. Okay. Another example you see here, like 27, right? So 27, like it's gonna replace the root that we are deleting, right? So if 27 goes here, then this was a max heap, right? We compare 42 and 23. 42 is bigger, right? So we pull 42 up. So you can think of this one as like swapping 42 and 27. That's possible. Or you can just like think of just like pulling this child up, right? And comparing 27 with the children of the node that's supposed to be here. So if 27 is here, then we compare like its left and right child. 35 is bigger. Now we compare 35 with 27. We need to do another swapping or another pulling the child up, right? And we get to this point, right? So this node only has one child, right? So like we compare 19 and 27, right? This satisfies the heap max order property. So then we stop here, right? You see that, like as opposed to the previous example, we didn't reach the leaf, right? But we stopped right here because we got to a point that the node satisfies the heap order property. Okay, so again, for deletion, the process that we follow is like from top to the bottom. So it's called bubble down or trickle down or reheapification down or sift down, like many different terms for it. You see another example here. You can go through this one yourself, but you can see that like this is for characters. You see that this one is again a max heap, right? So we remove the root, right? We remove the root, and what we do, we replace the last leaf or the last element of the array, right? Like here, like instead of the root. And then what we have to do, we just like have to bubble down or trickle down, right? We find like which one is bigger, S or M. S is bigger, right? And we compare S and O, right? S is bigger according to the ASCII table, so we swap S and O, right? So this one is showing swapping, right? Now we still have to go all the way down to a leaf, right? Or like we get to a point that the heap order property is maintained. Now we compare L and R. R is bigger than L, and then we compare R and O. Again, R is bigger than O, so we replace we swap these two. R comes here, O goes here. And at this time, like we reach the leaf, so like there's no further node, so like the heap is fixed, right? We deleted the node, and we maintained the heap order property. Okay, So the algorithm for this, again, it's very similar to what we did for insertion, but instead of going from bottom to the top, we go from top to the bottom. So again, we just like have to find, instead of finding the parent this time, like we have to find the left child and right child. We find like the like if here, let's say like if here we are implementing this for a min heap, right? So like we find the minimum number between left child and right child, right? And then we compare that number with the last element that was gone up to the root, right? And we keep doing this process until we reach a leaf, or like we get to a point that the heap order property is maintained. This also shows you the C++ implementation of it. Like it can be done like so. For bubble up, I showed you non-recursive implementation. This is a bubble down approach, right? And you see that like here we have um, again, here we also have recursive implementation. I noticed the error here. Okay, so like here it's also a recursive implementation of bubble down. This one, like if you implement this algorithm, like you can implement it non-recursively. This is the recursive implementation. This is the non-recursive implementation. So this one, it's just like basically the bubble down algorithm. Some people call it max hippify or like sift down, or like there are like many different terms, rehipification down. So like here you just like basically make sure that like once you have an array, you have the number of nodes and you have the index of a node. You just like basically do rehipification starting from this node downwards, right? So you're making sure that the node that the tree or the subtree that starts from this root, right, from this node at this index, um, it's it has the heap property. So like this is basically what it does. And for removing, as mentioned, we just like the last element is going to be taking over the root, right? The size of the heap is reduced by 1, and then we call the max heapify, right? So this is how the deleting work. Each step of a bubble up or bubble down, each of the iteration or each of the recursion takes order of 1. There are at most in the order of log n base 2 steps in bubble up or bubble down operation. Why? Because the height of a complete binary tree is in the order of log n. Okay, and so because of that, the insertion and deletion, like both of them are going to be order of log n. Okay, so another operation that we have for heaps is when we have an unsorted array, right? And we have an unsorted array and an unordered array, and we want to implement a heap, right? We want to implement a heap. So we want to make an array a heap, right? So this is basically, it's called heapify, like making like an array a heap, like heapify an array. So this has, there are two approaches for this. There are two approaches for constructing a heap out of an array. Okay, the first approach is called top-down approach. So if this is our array, so we assume that we have like an empty heap, an empty tree, and we start inserting elements of array one at a time. So we insert 3 into the heap, right, using the um, bubble up approach, right? So like you remember that like for insertion we did like bubble up approach. Okay, and the other one, and the next element is 1, so like we insert 1, then insert 8, then insert 14, 10, 15, 9, and so on. So this is one approach that we can have, right? The second approach is like implementing a complete binary tree, right, using this array, right? So like not caring about the order, but just like putting this one in the root, and then 1 and 8 in the level 1, 14, 10, 15, 9 in level 2, and the last 7 numbers in level 3, right? And then applying the bubble down approach. So the bubble down approach. So this is the second approach. We're going to go through both of them, and using examples we'll see like how both of these are going to work. So in the first approach, we insert one value at a time into the heap, right? So it's called the top-down approach. Push each new value down the tree from the root to where it belongs. The big O notation for making a heap out of an array using this approach is going to be order of n log n, because we have n elements in our array, and for each of them it takes log n operations to insert them, right? You remember that inserting a node into a heap takes log n. So, well, this is not an exact mathematical proof, but it just gives you an idea why this is the case. The second approach, we start with the full array, right? So like we basically put all the numbers in in a complete binary tree, right? So assume that like we already have a complete binary tree, and since nodes below like nodes below, I mean like the leaves. So like all the leaves form a heap, right? Because like every leaf it is a heap. So like we don't need to do anything with the leaf, but starting from the last parent, starting from the last parent, okay, we are gonna apply the bubble down approach. We're gonna apply the bubble down approach. So we're gonna just like need to push current nodes down, at worst go to the leaf. And because like we have a pyramid structure, most of the nodes are at the bottom, so we don't have much to go, right? So there's not far to go. And I'm going to show you the proof for like why the big O notation for the second approach is big O of n. Okay, I know that this is like confusing, but like we'll see through examples like how these two approaches work. Okay, so the first approach is that let's say that like just like we have an array, and like we keep inserting elements one at a time, right? We keep inserting one at a time, right? You remember that when we inserted like a node into a heap, right, the big O notation of that was log n, right? And now because our array has n elements, the efficiency of building the heap using this approach, which is going to be bubbling up, using like bubbling up, like going like from from here, like from the leaf all the way to the root, this is going to be big O of n times log n. So let's say that our array is 8, 10, 5, 12, and that's it. Like we have an array of like 4 elements, 8, 10, 5, and 12, and we wanna build a heap out of that. So first we insert 8, then we insert 10. Let's say that we want to have a max heap, right? So like when we insert 10, we insert it here at the last as the last leaf, right? As the last next to the last node, right? So like we insert it here, right? Then this is not satisfying the heap order property, so there is a need for bubbling up. So this goes up, right? So like here, like now we have a heap, right? Now we insert the third number, which is 5, right? And 5, it's going to be inserted here. Now we compare 5 and its parent 10, right? It satisfies the heap order property, so this is a heap with 3 nodes. Now we insert the last number, which is 12. Like 12, it's going to be inserted at the next to the last node, so it's going to be here, like to satisfy the structural property of the heap. Right now what we have to do, we have to bubble up. Like we compare 12 and 8. 8 is gonna slide down. Like we're gonna compare 12 and 10. 10 is gonna slide down, and then 12 goes in the hole here. So like this is like the top down example. We start from top, we go to the down. Like we start from scratch and we build the heap one element at a time. This shows you another example of the top-down approach. Let's say like this is our array 20, 40, 30, 10, 90, and 70. Again, like let's assume that we want to have a max heap. 20, we insert like only like one node, it is a heap. 40, it's going to be inserted on the left child of 20, right? So like this is like satisfy the structural property but doesn't satisfy the heap order property, the max heap order property. So 40 and 20 will be swapped. The next number would be 30. It's going to be inserted here. We compare 30 and 40, satisfies the heap order property, that's okay. Then we insert 10, right? It's going to be inserted next to the last node, so it's going to be here, right, at the end of the array. Like if you remember, like it's always like next to the last node. So this is still a complete binary tree, but it doesn't satisfy the heap order property. 10 and 20 is sorry, actually it satisfies the heap order property, so there is no need for swapping or sliding down. And then the next number to insert is 90. It's going to be inserted as the right child of 20. It is a complete binary tree, but 90 is bigger than 20. So like again, like we have to do bubble up all the way to the root. 20 is going to slide down here. 90 goes up here. Like we compare 90 and 40. 90 is bigger than 40 as well. So 40 is going to slide down this way, and 90 goes here. So this is what we have like after inserting 90, right? And the last number in the array to insert is 70. It's going to be inserted as the left child of 30, right? We have a complete binary tree. Let's compare 70 and 30. 70 is bigger, right? So like you can either swap these two, or you can just like basically slide this down here, like slide this parent down here. So 30 is going to come here. We compare 70 and 90, right? 70 is smaller than 90, so like there's no need to do any more bubbling up after this point. So like our recursion stops, or like loop stops, and like 70 goes right here. Okay. The second approach for building a heap, right? So this one as the bottom up approach. So let's assume that we want to implement a heap out of this array, right? This is not ordered, right? It's not even partially ordered, like, right? So like it's not satisfying the heap order property. But what we do, like we basically insert all the elements into a complete binary tree. Okay, so you see, like it is possible to do that. Okay, now what we want to do, like we mentioned that, like for a binary tree, for a complete binary tree to be heap, right, all its nodes should have the heap property, the heap order property. Now all the leaves of a binary tree, they have the heap property, right? Because like they don't have any children at all, right? So like they are all heaps, right? So what we do, we ignore all the heaps and we start from the last parent. So in this case 16, right? In this case 16, and we go down, we compare this one, like we bubble down, we trickle down, we sift down, right? So if this is like a max heap, like we compare 16 and 17, in this case there is no moving is needed, right? In this case, right, we first like find the, like here, like we have like the next node, the next parent, right? So like here is the, like the node at index 3 with the value 2. Okay, first, because we want to implement a max heap, right, we find the largest child, which is 14, and then we compare 14 and 2, right? 2 is smaller than 14, so like basically 2 has to bubble down. So 14 goes up, 2 goes right here, right? So 14 goes here, 2 goes here. Then we do exactly the same thing for the next parent, which is 3. Has 2 children. We find its largest one, it is 3. Sorry, it is 10. It's at index 6, right? So then we just like 10 is bigger than 3, so we have to swap them, or like slide this one down, 10 goes up here. Okay, and we do exactly the same thing for all the nodes, right? So like here, like we got here, like right now 14 is here, 2 is here, 10 is here, 3 is here. Now we get to this point, 1, right? So again, we find its largest child here, like we have 16, and like here, like if you remember, like 14 is up here now, so 16 is still larger. We compare 16 and 1, 16 is bigger, so like we slide 1 down, right? 16 goes here. We still have to go all the way down, right? So like we compare 1 and 7. 7 is bigger, so 7 comes up here, 1 goes down, and then finally we have to do the same thing for this one. Okay, so this is like the second approach that we have. Just like a reminder for you that the second half of the array are the nodes. So the nodes, the elements is starting from ceiling of n over 2 all the way to n minus 1 are the leaves, and we just like want to apply bubble down or trickle down or sift down or percolate down or max heapify down or heapification down on elements between 0 to floor of n over 2 minus 1, right? So like basically on the, just like only half of the nodes, right? Okay, and you see that because like we have such a pyramid structure in a heap, right? Like basically we don't have that way far to go, right? That much far to go. Okay, this shows you the algorithm or the pseudocode that you have to do for this one. This part is only for your information. it shows you that why this algorithm, the second algorithm to build a heap out of an array, is more efficient than the first one, right? So it basically shows you that at each step, right, how many operations that we have to do and what is the height, right, at that level, right, or at that level, yes, right, and how many nodes we have like at that level. So the total number of operations that we have to do, it's just going to be the number of nodes at each height multiplied by its height, and the summation over the summation of heights going from 0 all the way to the maximum height that we can have. Okay, and if we do this here, like this is the mathematical proof that just like shows you that if you calculate this series, we find that this is going to be of order n, as opposed to the first approach, which was of the order n log n. So this approach is more efficient. So again, like here, like to create a heap from an unordered array repeatedly, call bubble down. Any subtree in a heap itself should be a heap. Call bubble down on elements in the upper half of the array, right? Upper half of the array. So we start from the last parent and we go all the way to the root. We see like this is the upper half of the array. Okay, and bubble down does not need to be called on the leaves because the leaves are already heaps. This shows you how, like this shows you the complete algorithm or pseudocode for that. This is basically what we saw for bubble down, like exactly the same thing that we did for deleting, right? In deleting, we also did like bubble down, like we move towards the leaf, right? So this is exactly the same code, and we just like do this multiple times. We do this multiple times for all the nodes in the first half of the array. Okay, so here let's just like show you through an example. Like here, um, like if we just like want to apply bubble down for this um, heap, like let's say like it's stored in this array and starting from index 1, right? So like bubble down for this one is starting from index 1. Now here we have 18 here. We find we want to have a max heap, right? We find the largest child, which is 24. So 24 goes up here, 18 goes down here. Okay, so we compare, like we find the largest child again, it is 14. We compare 14 and 18, right? 14 is smaller, so it's at the correct location. So like this is what we have. Like this one, basically this has been heapified. This one has been heapified, right? And for like implementing a heap or building a heap out of an array, so we have to call this function multiple times, so which is like shown here, how to build a max heap. So you can either like do it non-recursively or you can do it recursively as well. This also shows you the implementation of build heap, or like this is also called heapify, implementation of it in C++. You see that like for all the parent nodes, starting from the last one down to the root, we are gonna call the bubble down or percolate down function. So example here, okay, so let's assume that we had an array was 4, 1, 3, 2, 16, 9, 10, 14, 8, 7. We inserted that into a binary heap, into the binary complete binary tree, right? So like we assume that that implementation represent a complete binary tree, right? We start from the last parent, okay? So we start going bubble down, like we compare like this one only has one child, so we compare 7 and 16. If we want to have a min heap, right, these are like in the wrong order, right? This doesn't satisfy the min heap order property, so we swap 7 and 16, right? The next parent, like we're starting from here, we go all the way to the root. The next parent is this one, 2. Again, we want to have a min heap, right? So like we find the smallest child, which is 8. We compare 8 and 2. This satisfies the condition, so we don't have to do anything. The next parent is 3, right? So again, like we start from the last parent and we go down to the root. The next parent is 3. Okay, we find the smallest child, it is 9, right? And there is like this doesn't violate the heap order property, so there is no need for swapping or sliding or pushing up. And the next parent node is 1, right? The next parent node is 1. Okay, so again for this one we compare, like we find the smallest child, which is 2, and 1 is already smaller than 2, so like we don't need to again like do any changes for this subtree either. So like you see that like we didn't need to do any swapping. Now finally we get to the root. Okay, at this point we find the smallest child, which is 1, right? So this is violating the heap order property. The heap order property is not satisfied for the root. So what we do, we swap these two nodes, right? Or we swap the two array elements, right? So 4 are gonna slide down, 1 goes here. Again, we find the smallest child among 2 and 7, right? 2 is smaller, so like 2 is gonna go up here, 4 is gonna slide down. We're gonna find the smallest child, which is 8, right? And 8 is bigger than 4, so like after this point we don't need to do any changes. So like our heap implementation stops here and we'll have our heap. This shows exactly the same procedure again. So we assume that this array represents a complete binary tree, right? We have all the elements like in the levels, like from top to the bottom, from left to the right. And we start looking at the last parent, right? Here, like we want to again like have a min heap, right? So here we want to have a max heap. We want to have a max heap in this one. So like we compare 13 and 11, doesn't violate, right? So we go to 19, find the maximum one, it is 14. This doesn't violate the heap order property. So we go to the next one, 3. We find the maximum child, the largest child, it is 16. We have to do swapping. So 16 goes up here, 3 goes down here, right? Then for this one here we have 1, right? So we find the largest child, which is 19, and 19 is bigger than 1, so 19 and 1 are gonna replace their, like are gonna exchange like their place, right? So 19 goes up, 1 slides down, right? And then if 1 is here, right, its children are 14 and 7. 14 is the largest among the children, so, and 14 is bigger than 1, so 14 is gonna go up and 1 is gonna slide down. So like this is like what we have like here, like after 19 and 1 swapped and then 1 and 14 swapped, so this is like what we end up with. And finally we have to go through the root. For root we have number 4, key value 4. We find the children. The left children is 19 and it's bigger than the right children, so, and it's bigger than 4, right? So then 19 and 4 are swapping. 4 is bubbled down or trickled down. Like here, like 4 is here, we find the left and right children. Okay, the largest one is 14, so 14 is bigger than 4, so 14 is gonna go up, 4 is gonna go down. And again we do the same process, right? Left child is 1, right child is 7, the largest one is 7, right? And 7 is bigger than 4, so we have to swap these two. And we started like we did like all the roots, and we bubbled down, sorry, we did all the parent nodes and we bubbled down all the way down, and the heap order property is now maintained. So this is the heap that we have out of this array. This again shows you the same example, like the same concept. So like here, like we ignore all the leaves, like these are already complete, these are already heap, right? So then we look at the like these parent nodes starting from 27, and like we have 11, 5 and 25. Okay, so like this part can actually be done like in parallel, right? So if you have multiple processors, you can do it like in parallel. So like in this example we show like changes happening to these subtrees at the same time. So we have these 4 parents, right? For each of them, right, we're gonna bubble down from this point on, like for this one as well, for this one as well, for this one as well. So here 23 and 20. So let me first figure out if we want to have a max heap or we want to have a max heap, or sorry, a mean heap. We want to have a mean heap. Okay, yeah, we want to have a mean heap. So here so 20 is smaller than 23, so we found the smallest child. We compare 20 and 27, we swap. Okay, 6 and 7, 6 is smaller, 6 is smaller than 11 as well, we have to swap. 4 and 12, 4 is the smaller child, 4 is smaller than 5, we have to swap. 15 and 16, 15 is the smallest child, and 15 is smaller than 25, we have to swap. So this is what's gonna happen. Okay, this is what's gonna happen. Okay, and so then like here, like we just like swapped like whatever needed to be swapped. Then the next level, like we go to the next parents, right? So starting from 8 and 9, so like both of them, like here, so like we have to do bubble down for both of them. Okay, so for this one we compare 6 and 20. 6 is smaller, 6 is smaller, so 6 is gonna go up here, 8 is gonna go down. Okay, I can't stop, I have to go all the way to the leaf, right? So like 8, I have to compare it with the smallest child, which is 7. So 7 is smaller than 8. So 7 is going to go up here and 8 is going to go down here. So you see like 6 went up here, 7 went up here, and 8 is going to be slipped down here. The same thing happening for this subtree. We find the smallest child, 4 is smaller and is smaller than 9. So 4 goes up, 9 goes down, right? We find the smallest child again. 5 is the smallest one, right? And 5 is smaller than 9, so 5 goes up, 9 goes down. So we would have 4, 5 and 9. See, like here, so like we just like have the swapping, and then finally we have it. And finally, we have to do the same thing that we did for the last parent, right? 4 and 6. 4 is the smallest one, right? So, and it's smaller than 14, so 4 is going to go up, 14 is going to come down here. 5 and 15, 5 is the smaller one, 5 is going to go up here, 14 is going to go up here, right? It's going to go down here, right? Sorry, bubble down here. And then so here like we have now like we just like end up having 4 here, then 5 here, then 14. And now the children of this node are 9 and 12. 9 is the smallest one and it's smaller than 14, so it's gonna swap, right? So like this is basically what's happening. 4 goes up here, 5 goes down here, and eventually 14 goes down here. And you see that like here like it shows like the implementation of bubbling down using just like creating a hole and pulling the parents down, right? So like this is, oh sorry, pulling the child up right here. Like what's happening here, we pull the child up, we pull this child up, we pull this child up, and eventually we insert this one at the correct location. Okay, this table shows the time complexity of some of the algorithms that we have seen so far, some of the sorting algorithms that we have seen so far. Let's focus on the heap part. For deleting or inserting, we realize that it's order of log n. If we want to build the heap, right, if we use the first approach, it was order of n log n, but the second approach is more efficient, so it's going to be big O of n. Okay, we're going to talk about heap sort in the next video, and you see that like heap sort is a sorting method used like that uses heaps, and it also has order of n log n, similar to quicksort and merge sort. Okay, so this is like one thing I forgot. Like if you want to find the minimum in a min heap or like finding maximum in a max heap, that's big O of 1. Like if you only want to find it, like if you don't want to remove it from the heap, like if you only want to know the value of it, it's order of 1 because it's at the root, right? But if you delete it, right, then you have to reheapify your heap, right? Because your heap might lose its, or like definitely loses its heap property, right? So like you have to do the process that we did for delete me. It's like a summary for all the big O notation related to heap that we've seen, except the heap sort that we're gonna see in the next video. One thing I wanted to mention is that one of the advantages of array representation of binary tree is less space overhead compared to link representation. So you remember that we can represent binary trees using linked representation, like that we would have 2 pointers, left child, right child. We also have a data part, right? One of the advantages of array representation is like we don't need pointers, so we don't lose any memory location for pointers. According to the tree theorem, if we represent the tree using link representation, half of the pointers are null. Half of the pointers are null. It's just like they're not pointing to anything. And you see that like if you have n nodes, each node would have 2 pointers, right? 2 pointers and a data part, right? So like we basically call this one memory overhead or space overhead, right? Because like in order to store all our nodes in the memory, we need to have pointers as well, like, but pointers like do not keep the values that we need, right? They're just needed for the linked representation. So this is called the overhead, the space overhead of linked representation of binary tree. Okay, so some other operations that we can do with heaps: return minimum in a min heap or return maximum in a max heap. So you just like basically have to return the value of a0 or heap 0. Okay, you're not changing anything, so this is like a constant member function basically. Other operation that we can do, we can change the called priority, or change the value of a node, right? So like in like, let's say like here, like we have a heap, right? And we want to change the value of this node, right? We call it also the priority or the key value of it, right? So like this is 15, right? We want to change it. Let's say that we want to change this node's value to 18. Like if we do that, like we can do it, right? If we do it, right, then like the structural property of course didn't change because we didn't remove or insert anything. Let's look at the order property, right? If you look at this one, right, 18 is smaller than 20 and 25, and 18 is bigger than 10. So like this like satisfies the heap order property, right? So there is no need for bubbling up or bubbling down, or percolation down or percolation up. Now let's assume that if I wanted to change this value of x to 40, right, then if x becomes 40, this is not going to be a min heap anymore, because 40 is not smaller than 20 and 25. So we have to go down, right? So like 40 is smaller than 10. Sorry, it's bigger than 10, but it's not smaller than 20 and 25. So what we need to do is like finding the smallest number in the children, the smallest children, the minimum children, and just that one is going to go up, for 40 is going to go down. So this is like what we end up. So like in this case we had to do bubble down. If we want to change the priority of x to 2, right, in this case, if we look at it, right, we have a min heap, right? So like here 10 is supposed to be smaller than x, right? 10 is supposed to be smaller than x. If x becomes 2, 10 is bigger than x. So what we are going to do, we're going to percolate up. So 10 is going to slide down, 5 is going to slide down, and 2 is going to go here. So if you are asked to find a function that changes the priority or the value of a key, you might have 3 different scenarios. The heap property might not be violated. It might get violated, and you might need to do bubble up, or you might need to do bubble down. Okay, so like these are like simpler methods compared to this one. This is a more general method, right? This is a simpler method. So like if you want to increase the value of a node, or if you want to decrease the value of a node, right? So like here, let's say like we have an array, and the index 8 of this array, which represent a heap, we want to make sure that this is changed to 1, right? So after this, like if it's changed to 1, if you're decreasing this, right, we have to make sure that the heap order priority property is maintained. So what we have to do, just like in this case, we have to do bubble up, right? So like 1 and 4, because we have a min heap, right? So like we had a min heap, we still have to have a min heap, right? There's swap, 1 and 2 swap, and 1 and 1, like we don't need to do any swapping, so it stops right here. And the same thing you can do with the increasing, right? So like these are like simpler versions of this one. You can also delete like any key, like not just the root, right? Not just the root. You can delete any key of the heap, right? Delete any node of the heap. The process is like basically you have to do like either you have to do a sift up, or like sift up is the same as bubble up, or you have to do sift down based on what happens after deleting that node, right? So like this is like something that you like I would like you to implement yourself. The algorithm is provided, but like you have to understand the algorithm and you have to implement it. Okay. So for heaps, right, if you want to implement them as a class, there are certain member functions that we want to have for them, right? So like we want to have insert or delete. You might want to have clear the whole heap. Like we want to get the size, right? The number of items in the heap. We want to know if the heap is empty or not. We want to get the first or next item, right, in level order from the heap. And is empty, is full. Like there are like many different methods that we can have. We can have a constructor, like a default, non-default constructor, and so on. This shows you an example of like a class declaration for heap, right? So like we have like here we have like a pointer to an array, right? So like we can have like we can assign the array dynamically. Like we have the size and max heap, the length and the size, right? Number of heap items and number of the array elements. Like we have the constructor, is empty function, insert, is full function, delete, get max, right? So like finding the maximum value of a heap max, getting the size, right? And clear the whole heap. Or you can also have like bubble up, bubble down approaches, right? So like all of them are some of the member functions that you can have for your heap. Okay, so this is like an introduction for the next video, that is heap sort. So let me go back to what we did in deleting, right? So like let me go back to what we did in deleting, right? So like we did insertion, we did, sorry, we did deleting here. Let's look at this one. Okay, so here, right, we like whenever we delete the root of a heap, right? So like we just like we replace the root with the last item, and we did bubble down, right? But what can we do with this one? Like what is the property of this one? The property of this one is that this is the largest number, right? And once we like let's look at let's look at this one. Let's look at this one. So once this is the largest number, once we delete the root, right? We in the same array that we have, like we have one less element because we deleted one of the elements. And this one that we deleted, we can just keep a temporary, we can keep that in a temporary variable, right? And after we did the bubble down approach, right, we can just insert the previous root at index 10, sorry, at index 5, at the last element, right? So like here 10, right? So like this is not part of our heap, but it is inside our array because our array has already have capacity for it, right? Because we will have one empty spot here, so we can insert the node that just got deleted. We can insert the value of it in this empty spot, right? And if we keep doing this, the next time we have like after doing the bubble down, we have this heap. So 9 would be here, 5 would be here, 6 would be here, 3 would be here, 2 would be here, right? So the next number to be deleted would be this root would be 9, right? So again, we would have one empty spot again. So we can insert 9 at index 4. And we keep doing this. So if we keep deleting the nodes of a binary heap, right? If we keep deleting the nodes of a binary heap and replacing the root at the end of the array, the whole array becomes sorted. So this is the main idea behind heap sort. So this is what we're gonna see in the next video. Missed it. Yes. So what we can do using heaps, we can implement a heap from an array. So we can just basically, using the heapify algorithm that we saw, right? We can just create a heap out of an array, right? We saw two approaches. One of them was big O log n, the other one was big O of n. So using the second approach, we can build a heap out of an array in the big O n notation, right? And then we just like keep deleting elements of deleting nodes from the heap. So basically deleting the roots. So we keep deleting the roots and replacing them at the end of the array. So if we do that, we basically, and if we repeat doing that, we end up with a sorted array. So this is like one of the applications of heaps that you can just like use them to sort arrays. So some problems that I want you to think about, like what is the maximum number of nodes in a max heap of height h? What is the maximum number of leaves? What is the maximum number of internal nodes? Assuming the data in a max heap are distinct, we don't have any duplication, what are the possible locations of the second largest element in a max heap? Let A be a heap of size n. Give the most efficient algorithm for the following tasks. Find the sum of all the elements. Find the sum of the largest log n elements. Right, so some problems that I want you to think about. These are some advanced topics that we don't cover in this course. There are different heaps that we don't see in this course, but if you're interested to learn more, you can learn more about min-max heap, double-ended heaps, leftist trees, binomial heaps, and Fibonacci heaps. Okay, thank you so much. That was it for